Hi everyone! For our senior design project, we worked on the computational modeling of solid solution hardening in aluminum alloys. My name is Ria, and I'm joined by my partners Martin and Yuri. So for our project need and objectives, our main goal is to compare the computational and experimental data for strengthening mechanisms in aluminum alloys. So we want to create the first principal density functional theorem computational models in order to determine the properties of aluminum alloys. And then we'd like to conduct testing of solid solution strengthening effects for aluminum alloys. So our main goal here is to create a data loop for the comparison between modeling and experimental data. And ideally, we would have accurate predictive models which would help accelerate material development processes for Army Research Lab and for other engineering companies. So the main mechanism is solid solution strengthening, and our computational approach is DFT. And experimentally, we're comparing pure aluminum versus aluminum alloys. So for our computational approach, we'll be looking at DFT, where the input is the atomic number and initial structural information for an element, and the output is the structural properties and electrical properties. And the software that we'll be using for the visualization of the supercells is VASP. Here we just have 4 possible ways that an atom can situate itself in an aluminum FCC matrix. So we have the Crowdian interstitial, tetrahedral interstitial, octahedral interstitial, and substitutional. As for our experimental plan, we'll have 9 samples per material, with the materials being high purity aluminum, aluminum 7075 annealed in air, and then aluminum 7075 annealed in argon. So all the samples will undergo some form of heat treatment, with the first sample being set aside as some form of benchmark. The second set of samples, 2 to 5, will be cold rolled by 15 and 30%, and then the third set of samples, 6 through 9, will be annealed a second time. Next, they will undergo prep, cutting, grinding, and polishing in order to go into the characterization phase, which will consist of visual light microscopy to determine initial grain size, Vickers hardness tests, and lastly, X-ray diffraction to determine dislocation density and analyze the phases.
This slide shows the microstructure of aluminum 7075 samples under different conditions. The image on the left shows the samples that has been treated for 20 minutes at 300 degrees C, which has a very fine small grain. The average grain size is about 20 micron. The second and third image shows the 400 degrees C in air condition and 500 degrees C in argon condition. The grain size increases with the temperature significantly. In this slide, it shows the final heat treating condition for both pure aluminum and aluminum 7075. The pure aluminum was annealed at 300 degrees C for 20 minutes. It resulted in these massive big grains with average grain size of around 600 micron. In order to get as large grain size as possible for aluminum 7075, the samples was heat treated under 550 degrees C for 12 hours. Which is the highest possible solution treating temperature without potential melting issue. The final average grain size is around 100 micron for air condition. In order to minimize the oxidation, we also heat treat the samples in argon, which results in a larger grain size. This slide shows the XRD results for both pure aluminum and 7075 samples. The peaks are produced by constructive interference of X-rays scattered at specific angles from each set of lattice plane in a sample. Higher intensity means small dislocation along that slip plane. For instance, the first peak in pure aluminum sample 2 is the highest peak, which means the most intense dislocation entanglement took place along the 111 plane, which is the close packed plane for FCC aluminum. We also observed several missing peaks in some samples. That is largely due to the surface texture produced from sample preparation. The crystallized size D is the size of perfect grains in a crystal, which can be calculated using the Scherrer formula. The diffraction vector delta K can be calculated using the second equation on the right. After obtaining both crystallized size and the diffraction vector, we can finally quantify the dislocation density using the first equation.
In addition to XRD, microhardness data was collected on our pure aluminum and aluminum 7075 samples that are heat treated in air. For the pure aluminum, it was observed that the hardness increased after 15% cold working, and a further increase was seen with 30% cold working. This increase is due to the dislocations piling up at the grain boundaries or entangling with one another, prohibiting further movement of other dislocations. The remaining samples under the same cold working conditions were then heat treated again, and the hardness values dropped back down to what was seen with the control sample. This was expected as recrystallization took place and new stress-free grains grew while the previous dislocations during cold working were annihilated. The aluminum 7075 samples follow the same trend as the pure aluminum samples, but the values are much higher due to the Hall-Petch relationship that predicts that as grain size decreases, then the yield strength increases. In the previous slides, it was shown how much larger our pure aluminum grains are compared to the aluminum 7075 grains. Because of this, the pure aluminum samples had less grain boundaries to pile up the dislocations, which led to lower hardness values than the 7075 samples. In conclusion, the DFT calculations provide us with the shear modulus of the aluminum alloys in this project that will later be used along with the concentration of solute atoms, Berger's vector magnitude, and lattice strain to quantify solid solution strengthening, and a comparison between the theoretical and experimental will be created. Also, the hardness of the alloys increased post-cold working and then reduced after secondary heat treating. For the constraints, it was difficult to obtain our initial aluminum alloys in time due to supply chain issues and needing alloys with very low solute concentrations that are not readily available commercially. For the future of this project, low concentration aluminum magnesium and aluminum zinc alloys should be tested experimentally and then compared to the theoretical work. A tertiary alloy of aluminum magnesium zinc would also be worth looking into, as well as aluminum silicon. Any transitional metal alloyed with aluminum would provide good experimental data and would match up well with the DFT calculations. After information is collected on the aluminum alloys, comparisons could be made with titanium alloy systems. This project will continue over the summer and following semesters by Dr. Alpay and Dr. Frame's research groups. They will continue to provide the Army Research Lab with useful data for their efforts in advancing materials for military use. Finally, a massive thank you to our faculty advisors Dr. Alpay and Dr. Frame for their amazing support, guidance, and mentorship throughout this project, as well as Dr. Jensen and Dr. Rindersbatcher from ARL for their help and support. Also, thank you to Cassidy, Kim, Ken, and Kevin for their help with DFT calculations, XRD data collection, sample prep, guidance, and constant availability to aid us during the constant obstacles we faced.